Good afternoon, everybody. Thanks for joining us for this webinar titled Closed Loop Control of Stepper Motors. This webinar is brought to you by Design World and presented and sponsored by Galil Motion Control. So before we get going here, I'll mention a few housekeeping points of order. This webinar will be available online at designworldonline.com, and all registrants will receive a copy of the webinar via email. Also, at the bottom of your screen, you'll see a number of widget boxes. These can be moved and resized to your unique preference. You can open, close, and change the layout as you like. There will also be a brief Q&A at the end of the webinar. And if you are watching this webinar on demand, you can still submit your questions, and we will get back to you with the answers. Lastly, if you're on Twitter and you'd like to tweet about this webinar, you can do so and use the hashtag DWWebinar. So a little bit about our presenters on the webinar today. So my name is Miles Budimir. I'm a senior editor for Motion Control with Design World magazine, and I'll be moderating the webinar today. And now a little bit about our presenter today. Michele Patel joined Galil in May 2014 as an applications engineer. Before coming to Galil, he worked as an electrical engineer for a consulting firm where his technical contributions focused on system integration with PLCs, HMIs, and software. Since joining Galil, he has provided direct support for OEMs with their motion control applications. He's directly involved in developing various methods for integrating Galil products with different PLCs. Michele holds a Bachelor of Science in Electrical and Electronic Engineering from California State University at Sacramento. So without further delay, I'll hand it over to you, Michele.
Good afternoon, everyone. Today we're going to be talking about various forms of closed-loop control of stepper motors. Here's an overview of what we will be discussing. We are first going to review some of the basics of how a stepper motor works, including their benefits and drawbacks. Then we're going to discuss the methods to address the drawbacks, which are endpoint correction, stepper position maintenance mode, closed-loop microstepping, and two-phase control like a brushless DC motor. In a stepper motor, the simplest mode is full step, where the phases are energized one at a time to move the motor through a full step. A stepper motor typically moves 1.8 degrees per step, leading to 200 steps per revolution. So long as the motor is adequately sized for the application and you're careful to account for any resonance, you're going to be accurate to within plus or minus a half step. Stepper motors operate in open loop, meaning there is no position feedback. Because it's open loop, the motor doesn't know how much torque is required, so the drive has to apply maximum torque at all times. This is inefficient and is the reason why stepper motors run very hot. But it gets the job done. Given enough time, the temperature of the motor is going to rise significantly. This is one of the key limitations of a stepper. Another limitation is that torque isn't available at higher speeds. Shown here is a typical speed-torque curve for a stepper motor. Notice how it works. The torque is relatively constant up to about 200 RPM in this case. Then it drops off until it reaches its maximum possible speed. Why is this? The answer lies in the physics of how the motor works. Based on the motor's electrical characteristics, there is a limit to how quickly current can be pushed in and out of the motor phases. This is dictated by the motor's inductance, which limits how quickly current can change from one value to another in the motor windings. Let's look at the current waveform when operating at low speeds, where you have plenty of time to reach the maximum current. The time between steps is much greater than the time it takes for the current to reach steady state based on the motor's inductance. Notice the inductor is affecting the current rise. It doesn't change instantaneously. So what happens when the time between switching steps is shorter? At higher speeds, you start to switch the applied current before the current can rise to the steady state. This results in a loss of torque at speed, which we call torque roll-off. As you can see here, we are switching the current before it reaches steady state. At this speed, the torque has decreased to a fraction of the maximum value. Therefore, there is a limit to how fast the stepper motor can go. At a high enough speed, the torque roll-off can become significant. When this happens, there isn't enough torque to do the work that the motor has to do, and the motor stalls. Stepping away from the physics of a stepper motor for a moment, let's discuss one of the big issues of operating stepper motors in their full step mode: coarse resolution. 200 steps per revolution is not that many steps. In order to get more resolution out of a stepper motor, some very smart engineers figured out they could energize the phases of the stepper motor partially. When this happens, the stepper phases fight one another, and the resulting position of the motor is the location where the two forces find equilibrium. In all cases, the number of steps is increased by further breaking that sine wave into more and more discrete microsteps. This gives the stepper motor the ability to have 2, 4, 8, 256 or more times the resolution it previously had. That takes the motor from 200 steps per revolution to tens of thousands of steps per revolution. This raises the question though, since stepper motors are open loop, how can we be sure that the position we command when microstepping is the position that we get? Given that the full step mode was accurate to within the full step, what can be expected for microstepping? In order to understand that, we first need to understand how each phase affects the torque applied to the motor. This slide shows the motor at 30 degrees with no current applied and there is no torque. Let's energize phase A with a positive current. The motor now settles at 90 degrees. If we now turn on phase B and turn off phase A, the motor settles at 180 degrees. What would happen if we powered on both phase A and phase B at the same time? For each unique combination of current through each of the phases, you will end up with a unique torque component from each phase. Notice at point P, the phases are equal and opposite. There will be one and only one position in the electrical cycle where the two torque components are balanced. Let's take a look at how this would work with an example. For a given angle, we can now compute the required current from phase A and phase B. Let's assume our desired angle is 120 electrical degrees. To determine the current required to reach this angle, we need to look at the equations that govern the system. The torque from phase A is equal to the cosine of the angle theta in electrical degrees times the current applied to the phase times the motor torque constant. The torque from phase B is similar, but with the sine of the angle theta. In order for the motor to reach a position, the two torque components, which are equal and opposite, must find equilibrium. The current applied to phase A would have to be 0.75 amps, and the current applied to phase B would have to be 0.43 amps. Now, all of this works fantastically in a world where there are no other forces to worry about. However, anytime an external force is applied to the motor, the endpoint position will be affected. So what does this all mean for the stepper motor? Let's use an analog of the inner workings of a stepper motor to visualize the concept. Here, the mass represents the rotor, and the springs represent motor phase A and motor phase B. Depending on how I energize the phases, the block wants to move a certain location, like we previously explained. Let's now add in an external force in the form of friction. See how as I attempt to move the motor, the friction in the system is resisting the motion, causing my end position to no longer match the ideal position. This is the main issue with microstepping. Because the two phases fight one another to control the stepper motor's position, if there are any external forces, the motor settles at a position which is not the desired one. Another issue stepper motors suffer from is resonance. Why do stepper motors resonate? When a step is commanded, the motor will move, and the momentum of the motor moving will cause it to overshoot. This overshoot is dampened out by friction and other forces in the system, as shown here. Our mass and spring system has the same behavior. As I change the position of the springs, the motor is pushed to a new position. As it moves, it gains momentum, causing it to overshoot and resonate. Systems with high inertia and low friction will show this behavior, as there is little dampening the resonance. So now that we understand how a stepper motor works, what it does well, and what issues it suffers from, how can we modify the way the stepper motor is operated in order to address the issues? In all cases, the method involves adding an encoder to the stepper motor so that some kind of position algorithm can be added. The question becomes, how specifically do we utilize the encoder to address some of the drawbacks of the stepper motor? The first approach is endpoint correction. This method is the simplest and helps address final position accuracy. The controller commands steps, and the assumption is that the motor has moved to the commanded position. But what if the motor didn't reach that position? That's where using a mode like endpoint correction can be beneficial. Let's go over how the mode works. The controller profiles motion for the stepper motor. The motor then moves based on the commanded steps from the controller. The controller will complete the profile. After the motor has stopped moving, the user can check to see if there is position error. If there is no position error, the move is complete. If there is position error, then a correction move is performed. Once the correction move is performed, the motor has reached the desired position. What are some of the benefits of using this mode? First, this mode works for any stepper motor that has an encoder. The encoder can be placed either on the motor or on the load based on the application requirements. The mode is extremely easy to use because it's easy to understand. This method does not require any tuning for stability. The motor operates as a stepper motor. To illustrate how this mode works, let's take a look at a stage that has been configured to operate with endpoint correction. For this application, we have a linear stage that is connected to a stepper motor. The motor has a quadrature encoder. We are going to have the stage perform a series of moves. Due to the friction of the stage, the motor does not reach the commanded position of each move. Here we have a stage performing a series of moves. The dark red line is the reference position. The blue line is the actual motor position. The green line is the commanded steps from the controller. And finally, the brown line indicates that the controller's profiler is active. Each time the motor makes a move, it's off by over 70 counts. Now we're going to profile the same series of moves as before, but this time we're going to use endpoint correction. We will issue a correction move that is the exact same value as the error magnitude. If we take a look at the scope capture at the commanded position, actual position, and motion profiling signal, we see that after the initial commanded move is complete, the controller issues another move. The position error following the correction move is 0. While endpoint correction is effective in addressing position error, it is not a continuous mode of operation. The correction only takes place after a commanded move is complete. Endpoint correction wouldn't be able to detect if the motor had stopped while motion was being profiled. If there was a stall, how would you know? We can address this by using the next method of stepper control, the stepper position maintenance mode. The stepper position maintenance mode executes an internal monitoring of the stepper motor's commanded position and the motor's actual position, as reported by the encoder. The controller will then continuously monitor the position error to determine if the error exceeds the limit of 3 full steps. If you've slipped more than 2 full steps, you've slipped into the previous electrical cycle and a stall is occurring. This mode is good for detecting and reporting stall conditions, but not for correcting them. If you need to continuously correct for position error, you would want to use one of our next methods, closed-loop microstepping. This is the first true method of closed-loop control. With this mode, the commanded motion is a function of the reference position and the actual position reported by the encoder. The controller generates an error signal internally and uses it to continuously adjust the motor's position. The controller still generates step pulses to drive the motor, and the motor still operates as a stepper. The user has to set tuning parameters to use the mode. In order to get an idea of how this mode works, let's take a look at a block diagram representation. The controller first sets the reference position. That position value then goes through a closed-loop microstepping filter. This closed-loop microstepping filter has tuning parameters that must be set by the user to achieve system stability. The reference position is then converted into steps that are sent to the driver. The driver applies the appropriate current to the motor's phases to move the motor to the commanded reference position. The motor moves and then applies a torque on the load. As the motor moves, the encoder is moving, tracking the position of the motor. This position feedback is sent back to the controller. This whole process runs continuously. One thing to note is that the closed-loop microstepping filter has 2 sets of unique tuning parameters for when in motion and when not in motion. The controller will apply the parameters based on which state the motor is in. What are some of the advantages of using this mode? Because we're still driving the motor as a stepper, this mode is ideal for systems that do not require fast responsiveness to position error while in motion. As the motor moves, the controller will continuously account for any position error and adjust the commanded reference position accordingly. The user does not have to command anything besides moving the motor. Unlike endpoint correction, a correction move does not have to be issued after every move. Since the position error is continuously corrected, the motor is closer to the actual commanded position during motion. This reduces the total move time. Also, unlike brushless servo motors that can dither when settling at a target position, this mode can be turned on and off. So when stopped, you can lock the motor, eliminating dither. Let's take a look at a system running with this mode enabled. For this demo, we have a linear stepper motor with a quadrature encoder. We're going to run through a series of representative moves. First, operating in open loop, then we'll close the loop, and then finally we'll optimize the closed loop for performance. Here we have the motor moving in open loop. The dark red line is the reference position, the blue line is the actual motor position, and the green line is the commanded steps from the controller. Finally, the brown line is an indicator that the controller's profiler is active. There is a position error of over 130 counts during the move. By enabling the closed loop microstepping mode, we can improve the performance. Now that we've enabled the closed loop microstepping mode, we've also added a line to the capture. The black line is the position error, which is the difference between the actual position and the commanded reference position. Note that now there is only a position error of 65 counts during the move, and the motor settles within 48 milliseconds. By optimizing the tuning parameters, we can see that now during motion, the position error has been reduced to 5 counts. Settling has been reduced from 48 milliseconds down to 21 milliseconds. Now that we've seen what the mode can do, there are a few things to consider. Closed loop microstepping is good for systems that have low bandwidth requirements. However, it cannot match the performance of a high bandwidth servo system. While using closed loop microstepping, the motor is still operating as a stepper. This means that the motor phases fight each other to position the motor. This is not an efficient process for driving the motor. To address both of these issues, the next method of closed loop stepper control, two-phase brushless, should be used. With this method, we're no longer operating the motor as a stepper, but as a brushless DC motor. Normally, a servo has 3 phases. This mode works with the 2 phases of a stepper motor. When running in this mode, the motor can be stabilized the same way as a typical brushless servo. In this detailed block diagram, we can see all of the different tuning parameters that can be used to achieve stability and minimize position error. However, in order to understand how the mode works, we can look at a simplified block diagram representation. First, the controller sets a reference position, which is input into a closed loop filter. This tuning filter will then send a voltage command signal to the amplifier. Conceptually, this looks the same as closed loop microstepping, but the operation is different. In 2PB mode, the driver is now a transconductance commutating amplifier. The controller doesn't command steps, but instead commands a voltage signal that is directly proportional to the desired torque. The amplifier then produces only the current that is necessary to achieve this torque. This current moves the motor, and then while the motor moves, the encoder moves. The position data then gets sent back to the controller. While this is like a brushless servo, the motor mechanics are different and require a different form of commutation. A stepper motor needs 2-phase sinusoidal commutation to commutate the motor. This is similar to the 3-phase sinusoidal commutation that is used to commutate brushless servo motors. With 3-phase, the motor phases are 120 degrees apart. In 2-phase, the motor phases are 90 degrees apart. Recall in microstepping, the phases fight each other to create an equilibrium, while in the 2PB mode, the amplifier is sending the current to produce a torque that is the sum of the torque components from the motor phases. This is inherently more efficient. The amplifier switches current through the motor phases based on the actual position of the motor shaft within its electrical cycle from 0 to 360 degrees. Most 3-phase brushless servo motors have 2 magnetic pole pairs, so they would have 2 full electrical cycles per revolution. For the 2PB mode, we are using stepper motors. A 200 steps per revolution motor has 50 magnetic pole pairs. With the higher number of pole pairs in the stepper, the amplifier has to push current in and out 50 times per revolution. As a result, the stepper motor can only achieve slower speeds. However, it can get more torque because the electrical cycles are much closer together. This creates a gearing effect. It would be similar to having a brushless servo motor with a gearbox attached to it. To use this mode, there are some system requirements that have to be met. In order to achieve high bandwidth, the encoder must be mounted on the back of the motor, just like a brushless servo. This eliminates any resonance between the motor and the encoder. Also, the encoder must have sufficient resolution to allow the amplifier to properly commutate the motor. This means there must be at least 8 quadrature states per electrical cycle. For example, say we had a 200 full step per revolution motor. It would require an encoder with a minimum of 4,000 quadrature states per revolution. With 2PB, the performance is comparable to a brushless servo. It is good for systems with requirements for high responsiveness. Unlike normal stepper operation, where the current needed for maximum torque is applied at all times, the amplifier only applies the current that is required at any given time. This results in a more power-efficient system. By using a commutating amplifier to switch the current through the phases, the motor runs with significantly reduced torque ripple compared to operating as a normal stepper. In the following demo, we will be using the same linear motor we used with the closed-loop microstepping mode. This will give us a direct comparison of the performance that we can achieve with two-phase brushless. Now that we're running the 2PB mode, we're also going to want to take a closer look at the commanded torque, shown here in the bright red line. As the motor moves back and forth, we can see that the position error throughout the move remains very low, close to 2 counts. The motor's total move time is also less than that of closed-loop microstepping. The motor settles here within 4 milliseconds rather than 21 milliseconds. At lower speeds, the performance of a stepper motor running with the 2PB method is similar to that of a brushless servo. Both have good performance with no position error at the end of the move. The servo settles within 1 millisecond, and the 2PB motor settles within 4 milliseconds. The differences between a 3-phase brushless servo and a 2-phase stepper motor become clear when comparing the speed-torque data. Stepper motors can provide a great amount of torque at lower speeds, however, they are going to be limited in their overall speed. A 3-phase brushless servo motor can achieve higher speeds. Now we can get a direct comparison of the motor's performance with both the 2PB mode and the closed-loop microstepping. The two different methods yield significantly different operating temperatures. While the closed-loop microstepping method operates as a stepper, the 2PB method only applies the current that is required to hold position and move the motor. As a result, the mode is power efficient, and overall heat is significantly reduced. There is a difference of over 67 degrees between the two. What are some trade-offs to consider when using the 2PB mode? Stepper motors have more cogging than a brushless servo motor. Stepper motors also have an inherent limited speed of operation. One of the key benefits of a stepper motor is its low cost, but by adding a form of position feedback with an encoder, the overall cost will increase. But the stepper motor system will still be lower cost than a servo. Why not use a brushless servo motor? Servo motors can achieve higher speeds, don't have cogging, and are available in larger sizes. But with the 2PB mode, you can achieve high torque at low speeds for a lower cost. In summary, there are 4 methods of closed-loop control for stepper motors. Each method is applicable in different situations. Endpoint correction works with any stepper motor with an encoder, it's easy to use, and provides endpoint accuracy. This is available as a standard feature on the Galil controllers. Stepper position maintenance mode detects stalls and reports the position error. This mode can be used in conjunction with the endpoint correction and is also available as a standard feature at no cost. Closed-loop microstepping provides continuous error correction while operating the motor as a stepper. It's ideal for systems that have low bandwidth requirements and for systems with a load-side encoder. This method is available on Galil controllers as an orderable firmware option. Two-phase brushless is ideal for systems that require high bandwidth. It is a power-efficient mode where the motor operates as a brushless servo. Two-phase brushless is available as an orderable hardware option. All right, now it's time for some questions. We're going to go through the questions that people have submitted while watching the webinar, and just going to take a look through here and try to answer them. There's a lot of good ones in here. Okay, first question. So you've talked about the power dissipation of the stepper motor, but can't you lower the current when it's not moving? Yes, you can. So you can lower the current when the stepper motor is not moving. The Galil controllers have a low current setting that can be configured for any stepper motor. The user can specify if they want the current applied at rest to be 0 or 25% of the rated value. This will help reduce the heat, but when you're in motion, you still have full power dissipation, so the motor will still get just as hot. Okay, next question. I noticed in one of your slides that there are 2 sets of parameters for closed loop microstepping. Why is that? Okay, that's a very good observation, and basically the parameters for motion are optimized for smooth motion and low position error. And then when you're stopped, you want parameters that guarantee fast settling time with no position error and like maximum stability. So as a result, closed loop microstepping mode has 2 sets of parameters, so you get good performance while in motion and while stopped. Okay, next question. Why does a stepper motor have more clogging than a servo? Okay, that's a very good question. So a servo motor is designed to be a servo, and what this means is that low clogging is a requirement of being a servo. As a result, the manufacturer skews the laminate and moves the magnet from its favored position. This adds to the manufacturing cost and reduces clogging. Now, a stepper motor is designed to be as cheap as possible, and for most stepper applications, the clogging won't matter. And so as a result, most stepper motor manufacturers don't skew the laminate, and that's why you have more clogging in a stepper motor. Okay, next question. Okay, so you said that brushless motors come in larger sizes. Why aren't steppers available in these larger sizes? So as stepper motors increase in overall size, the current required to operate them also increases. As we said, steppers are power inefficient. In small motors, this can be tolerable, but as you get larger and larger, the amount of current required and the heat that's produced become prohibitive. And so while stepper motors could be made in larger sizes, there's simply no demand. Okay, oh, here's a good one. So how does this discussion apply to different types of stepper motors other than 2-phase, such as 5-phase, variable reluctance, or operating the stepper in unipolar mode? Okay, so the first 2 methods of endpoint correction and stepper position maintenance mode, those can be used on virtually any type of stepper motor. They're simple, and the stepper motors have all of the same operating characteristics to make the modes work. Closed loop microstepping itself, that's usually reserved for bipolar stepper motors, and therefore it's not applicable to other forms. And the 2PB mode is a unique result of the architecture of the 2-phase brushless motor, and therefore it's not applicable to other forms of steppers. Okay, all right, let's see. I think we've got time for 2 more. Okay, it sounds to me that I should always use 2PB mode. When would I want to use closed loop microstepping? That's a great question. So there are 2 main reasons to favor closed loop microstepping in certain applications. First, if the encoder must be mounted on the load, this is practical with closed loop microstepping, but not with 2PB. The other is that it's actually a unique characteristic, the inherent fact that the motor is still operating as a stepper, and that when it stops, you can turn the mode off and guarantee that there will be absolutely no dither under no circumstances. This, for instance, would be ideal in an application where you're moving into a position and you're doing something with optics. It could be a scan, it could be a read, it could be, anything that's involving optics. You wouldn't want motion to be still occurring after you reach the position. So in situations like that, you would want to use closed loop microstepping. Okay, final question. How does the cost compare for the various modes? Okay, so the stepper position maintenance mode and endpoint correction methods are available as standard features on the Galil controllers at no extra cost. The closed loop microstepping firmware has a nominal one-time firmware fee. And finally, the 2PB option has a small per unit charge, and it's an orderable hardware option. Okay, so that's all the time we have today for questions. If you submitted a question and I didn't get a chance to answer it, I'll be emailing you within the next day or two. And if you didn't submit a question and you have a question on anything that we've talked about in the webinar, feel free to send an email to support@galil.com. And thank you very much.
So thanks for that informative presentation, Kushal. A few more points here before we wrap up. Keep in mind that this webinar will be available online at designworldonline.com, and all registrants will receive a copy of the webinar via email. You can tweet about the webinar using the hashtag DWWebinar. You can also connect with Design World through many of the usual social media outlets, including Facebook, Twitter, LinkedIn, Google+, Pinterest, and including our own engineeringexchange.com. And lastly, we'd just like to say thank you to everybody for attending today's webinar, Closed Loop Control of Stepper Motors, and wish everybody a good rest of the day.